All right, lesson 10.3 is about applying properties of chords, and we've already talked about a chord and defined it in lesson 10.1. A chord is a segment that touches the circle twice, and it goes through the interior of the circle. So we're going to draw a chord and label it AB. All right, now then, the next part of the instructions say to create an arc and a semicircle. Well, to create a semicircle, we've got to draw a diameter. So we create the center of the circle, drawing a chord that goes through the center, that's being your diameter. We're going to label that point D. Now, over here on this half of the circle, put point C just anywhere there. Okay. Now, if we're going to name an arc, there's three different kinds: minor, major, and semicircle. So we started off with a chord, and we call our chord AB with a segment on top. We've got a minor arc, several. We'll name this one right here, minor arc AB. Remember, a minor arc has to be less than 180 degrees, less than half a circle. A major arc is over 180 degrees, over half a circle. Well, and you need to use three letters also. If we start at point A, we can go to point D and then on around to point B. That would be considered a major arc. A, D, B, because it's over half of the circle. Then to create a semicircle, you use three letters again, but you just use half the circle. So since this is a diameter, we can use this half or this half. And you can go either direction, BAD or DAB. I'll just spell out a word, bad, with an arc mark on top. All right, now, the reason we went through this vocabulary is because all of these chords and arcs have similarities whenever they're in the same circle. If you have, and this goes on to the next theorem, in a circle, if you have congruent arcs, then you have congruent chords. And then you can have congruent central angles. You can also read this backwards. Congruent central angles create congruent chords, which create congruent arcs. All three of these are related. Okay? So looking in this first picture, we have two congruent chords. There's one, there's the other. And we're going to label this first chord as AB and the second chord as CD. Now notice that this arc right here that was created from chord AB is 60 degrees. Therefore, arc DC is also 60 degrees because the chords that created them were the same length. That's what this is talking about right here, that if you have congruent arcs, you have congruent chords, or if you have congruent chords, then you have congruent arcs. Now, the second picture, before we go on, let's create a statement with this. If segment AB, and that's your chord AB, is congruent to segment CD, which is your chord CD, then the measure of arc AB is congruent to the measure of arc CD, what we had just stated. The next picture, all right, you've got congruent angles. This central angle here and this central angle here are congruent. Now, according to this theorem, if you have congruent central angles, then you have congruent chords that are created from those angles. So if you look right here, this is a radius, this is a radius, and this is a radius. And they create these chords here and here. So this chord is formed from this central angle, the radii that form that central angle, and this chord is formed from that the radii that form that central angle. So what we're saying is that these two chords are congruent simply because their central angles are congruent. Also, we have arcs that have been created, ZY and XY. And since these are created from the congruent chords, they are congruent, or from the same central angles, congruent central angles, then these arcs are congruent. So what we're going to state here is if angle ZPY is congruent to angle YPX, then segment ZY is congruent to segment XY. And the measure of arc ZY is congruent to the measure of arc XY, which is here and here for the arcs, the chords, and the angles. All right? The last one. Here we've got the measure of arc BD is 150 degrees. Arc BD is a minor arc. Goes across there. It's 150 degrees. We want to find the measure of arc AC. What I need you to notice is that this arc is created by chord BD. BD has two segments marked off. AC is also a chord, and it's got the same segment lengths marked off. Therefore, BD is congruent to AC. Since those two chords are congruent, they create congruent arcs. Even though they're not in the same place, the arc measures are congruent. So it would also be 150 degrees as well. Okay. The next theorem. In a circle, if a diameter is perpendicular to a chord, then it bisects the chord and its arc. All right, so here's our circle. Here's our diameter. Okay, let's go ahead and label that. That's your diameter. And this is your chord. Now, it says if it is perpendicular, meaning it created a right angle. So if these two are perpendicular, then it bisects the chord. So the diameter bisects the chord, cuts it in half, and its arc. Here is the arc, so it also cuts it in half as well. All right, and it has to be because it's a diameter. If it was over here and didn't go through the center, it wouldn't cut that in half. Or if it was a diameter, but it wasn't perpendicular, it wouldn't cut it in half. So it's got to do both of those. It's got to be a diameter and it's got to be perpendicular. So our statement we're going to make based off of this theorem is if segment AB is perpendicular to segment DC, then, I need y'all to put a point right here. My letter E disappeared. Okay. Then DE, segment DE, is congruent to segment EC. And that's what we have marked here. These two segments are congruent. And the measure of arc DB is congruent to the measure of arc BC. These two arcs are congruent as well. All right. Next example, to practice that theorem, we say ZY, this chord here, is 6. Well, if you notice this right angle, that means this diameter is perpendicular to it. It splits this in half. So each one of those sides is 3 because half of 6 is 3. All right. XW is 4, so from X to W is 4. So this side is 4, and if you notice, we created a right triangle. We want to find the length of xy, which is this side over here, and xz, which is this side over here. Well, this is a 3, 4, 5 right triangle. And on this side, a 3, 4, 5 right triangle. If you needed to do Pythagorean theorem, you could to find its length. But remember that pattern. If it's a right triangle and your legs are 3 and 4, that hypotenuse is always going to be 5. Then it also wants us to make an assumption about YV and ZV, arcs YV and ZV. We can't determine what their measure is because we don't know the degree of the central angle that creates it. However, we do know that those two arcs are congruent because they are cut in half based on this diameter being perpendicular to that chord. Okay, the last two theorems now. If one chord is a perpendicular bisector of another chord, so right here, here's a chord, it's a perpendicular bisector of the other chord, meaning it's perpendicular, creates a right angle, and it cuts it in half. And notice the arcs were marked as congruent, so we knew it cut that arc in half. Then the first chord is a diameter. We're saying that this has to be a diameter if it's perpendicular and it's a bisector. That would just be your converse of this one here. This one we're stating it's a diameter that's perpendicular, so therefore it bisects it. Now we're saying it's a perpendicular bisector, therefore it's a diameter. So our statement that we're going to write based on this is if segment AB is a perpendicular bisector of DC, then AB is a diameter. Last but not least, in a circle or in congruent circles. So we can have everything in one circle or two separate circles. Two chords are congruent. Here we have chord EC. Here we have chord AG. These two chords are congruent if and only if they are equidistant from the center. Equidistant. All right, here's the center. So from here to the chord, from here to the chord, they are equal in length. So that's what these markings are for. So PF is the same length as PH. However, the H disappeared, so we need to draw in the H for this point right here. Okay, now realistically, if this chord was closer to the center of the circle, it would have a longer stretch to go across, making it longer than this one. If it was further from the center, it would have a shorter stretch from one end to the other, making it shorter than this one. That's why if they are the same distance, then they have to stretch the same distance across. That's what makes this theorem a true statement every time. So we're going to say if segment HP is congruent to segment PF, then segment EC is congruent to segment AG. And that's the end of these notes. Thanks, guys.